welcome back. We'll continue the discussion on the conservation law. In today's lecture, we discuss interaction of waves. So as we go along, I will explain what does that mean. So again, consider this conservation law ut plus f of ux equal to 0 with initial condition ux0 equal to u0x. So we'll be introducing some new terminology, and many of you might be listening to this topic of conservation laws. So you should study carefully and digest all this new terminology and also the results. Okay. So if the initial condition is given by just two constants, ul for x less than 0 and ur for x greater than 0. Okay. Such a problem is called a Riemann problem. Okay. Obviously ul not equal to ur, so if ul equal to ur, then it's just a constant and the constant is the only solution. Okay. So in general, if we take this bounded u0, it is possible to break the x-axis into small intervals where we can approximate u0 by some constants. Okay, for example, taking either maximum in that small interval or minimum. Okay, and this are the building blocks for a general initial value problem, and a numerical scheme called Godunov scheme is based on the solution of the Riemann problem, and that is Godunov scheme is also used both for computation as well as for theoretical purposes. Okay, so we start with this discussion of Riemann problem. So we take this initial function consisting of two constant states. Okay, so we refer to them as constant states. So yesterday, for example, we in the previous lecture we discussed by taking u0 equal to 1 0 for x less than 0 and 1 for x bigger than 0, and we obtained a solution for that problem. And in fact there were many solutions, so let me recall that. Okay, so this was the Burger's sequence. For Burger's equation we took it. So same thing holds for if you take any general f. Okay, so characteristics, the method of characteristics yields solution everywhere except in this region, namely 0 x less than t. So that region there are no characteristics. So then we obtained three solutions. Okay, but two were rejected because they did not satisfy the entropy condition. So entropy condition we'll see later that can be very neatly stated as an inequality. Okay, so again let me write that solution. Okay, so if now I take any ul and ur with ul less than ur, so you can easily check that for t positive, if I define this the function u by this relation, so it is ul if x by t less than 0, and this converse combination if 0 less than x by t less than 1, and again this constant state UR if x by t is bigger than 1. Okay, and we observe that u is a continuous function, so it's at x equal to t, it's at x equal to 0 it is continuous, and x equal to t also it is continuous. Okay, and this solution is referred to as a rarefaction wave. Okay, so I was talking about terminologies. Okay, so this is one terminology. So such a solution is referred to as rarefaction wave, and we say that the constant states UL and UR, when UL is less than UR, are connected by a rarefaction wave. So here is the in the XT plane uh, depict the characteristics, and this is also called a fan wave, so it looks like a fan here. Okay, so on the left it is again the constant at UL, and again on the rightmost it is constant at UR, and in between we have this fan wave. Okay, so entire thing referred to as rarefaction wave. Okay, so and UL and UR connected by this rarefaction. So what happens if we take UL bigger than UR? Okay, that's another case. Okay, for example, let's take simple case UL equal to 1 and UR equal to 0. And again, if you go back, so for most of the time I am assuming that f of u is, so it's a Burger's equation. Okay, so you can also uh, f of u equal to, so this is the Burger's equation, and so again you see, if you draw the characteristics in this case, when I take that initial condition with the left state as 1 and right state as 0, we immediately see that the characteristics intersect instantaneously. Okay, so characteristics coming from x less than 0 instantaneously intersect with characteristics. So these blue lines are the characteristics. Both are, this is for characteristic curves. So in this case they are straight lines, and these are also characteristics. Okay, so we have to uh, fit in a discontinuous curve so that we obtain a solution of the given initial value problem. Okay, and for that, so what should be the discontinuity, the line of discontinuity or curve of discontinuity? So we have already seen that it has to satisfy the jump condition. Okay, so this sigma, the shock speed, which is also denoted by, so this is the uh, discontinuous curve we are using. X equal to S. Okay, and sigma is its speed, and it has to satisfy this is jump condition. Okay, so this is just jump condition, and for the Burger's equation it is precisely the average of the left state and the right state, and this is of course equal to half if I take UL equal to 1 and UR equal to 0, Otherwise also it's just a constant, because our initial condition consists of only two constant states. Okay. So in this case, the solution is given by u of x t equal to 0 if x is less than sigma t, and 1 if x is bigger than sigma t, and sigma is the shock speed. Okay, so in general, if you take UL and UR as the constant states, then we get the solution as UX t is equal to UL if x is less than sigma t, and UR is if x is bigger than sigma t, and sigma is given by this ratio f of UL minus f of UR divided by UL minus UR. Okay. So again in the xt plane we see that, so this is x equal to sigma t, this is the shock or discontinuous curve. In this case it is a straight line. Okay. And in this case, so we have this, we say that the constant states UL and UR, where UL is bigger than UR, are connected by a shock wave. And shock wave, this is the solution is referred to as shock wave. So it has again two constant states now separated by a line of discontinuity. Okay, in general this need not be a straight line as we see in an example. Okay, so this is shock. Okay. So this is fine. So Riemann problem we can simply solve in either case. So either we'll get a rarefaction wave connecting the two given constant states, or they can be connected by a shock wave. Okay. Our next question is, what happens if there are interaction of waves? So there is a rarefaction wave and then there is a shock wave. Suppose they interact. Okay, there is some interaction. So here is a simple example. Okay, so quite illustrative. So you should study it carefully. And you see there are some complications here. And the more we appreciate such examples, we better understand the Lax-Oleinik formula, which hides all these computations. Okay, so Lax-Oleinik formula, which we are going to derive in due course, hides all these computations. Okay, so it's a very neat formula, but if you want to do something by hand, we see there are lots of computations and also some analysis. Okay. So now we consider this example again, Burger's equation. So ut plus ux equal to 0 and ux0 is equal to u0x. And now, so u0x consists of three constant states. Okay, so just for the illustration, so this is x-axis, so this is 0, this is 1, so this is 0, 1, 0. Okay, that's the initial condition consisting of three constant states. Of course, in the absence of this third constant state, if we just consider the first two, and since 0 is less than 1, those two states are connected by a rarefaction wave that we saw just now. And again, in the absence of the first state, namely this 0, x less than 0, so we make it 1 through x less than 1, okay, just like that one. Then those two states will be connected by a shock wave, okay. So we expect the solution to have a combination of rarefaction wave and a shock, okay. So indeed uh, that is happening, okay. So thus for T positive, so we obtain this solution. So the first two states are connected by rarefaction, and that's what I'm writing here. So uxt is 0 if x is less than 0, x by t if 0 is less than x less than t, and 1 if t is bigger than x. So in the absence of third one, that would have been the solution, okay. But since now there is another third state, and that has to be connected to the middle state by a shock, and again you see the shock speed has to be, since we are in Burger's equation, so average of these two, and that is precisely half, and that's what we get. So 1 if t less than x less than 1 plus t by 2, and 0 if x less than greater than 1 plus t by 2, okay. That shock speed is again half, okay. So this would have been all right, but we see some difficulty, okay. So if you consider this shock line, okay, in this case it's a straight line, so that is x equal to 1 plus t by 2, and this characteristic x equal to t coming from the rarefaction region, okay, they two intersect at t equal to 2, okay. And again, it's not possible to continue the solution keeping this x equal to 1 plus t by 2 line as a shock, because that will violate the uh, jump condition, okay. So why it is violating jump condition? So that's a simple computation here. So in case this, again this line has to be continued as line of discontinuity, its speed will be half, but if we take the left limit, that will be 1 plus t by 2 by t, and again ur is 0, okay. And if you calculate this ratio, okay, again f is Burger's equation here, so it's half u square. So we get that this ratio is not half for t bigger than, okay. So this line cannot be a discontinuity curve, as the uh, jump condition is violated. So this is valid solution only for t less than. Okay, so beyond 2, we have to again now construct a line of discontinuity or curve of discontinuity in order to complete the solution for t bigger than 2, okay. And again the jump condition is our guiding principle, so we'll try to find what should be the speed of that discontinuity curve beyond t equal to 2, okay. So we have to now uh, find that curve x equal to ct, which will accommodate the jump condition, okay. So again remember, we are in the Burger's case, so this s dot t, so which would be also denoted by sigma, that is half of ul plus ur. Okay, this ur is 0, that third state is 0, just remember that third state is 0, and ul is the limit of the solution as we approach the line of the curve of discontinuity from the left. Okay, so that is x, I should also say that, from the left, and that gives you st by t. Okay, so this curve of discontinuity should satisfy this ordinary differential equation, namely s dot t, just remember that s dot t is ds by dt. So solving this ODE and giving this initial condition s2 equal to 2, because they meet there, s at t equal to 2 should have 2 there. Okay, and one easily solve that ODE to get this solution. And first thing we should observe is that this is not a straight line. Okay, so here is the picture in the xt plane, characteristics, shock curves, etc. So up to t equal to 2, so there is only this rarefaction wave. So this is 0 here. This is x by t solution. Okay, and here this is 1 and again 0. And beyond t equal to 2 is now given by again 0, 0 for x less than 0, and in this region it is simply x by t. Okay, 0 x less than 2t to the half. Okay, then that is our new shock curve, and beyond that again it is 0. Okay, so since this shock curve is constructed to satisfy the jump condition, so there is no need to further check that, so it's automatically satisfied, and we have this solution. Okay, so now let's analyze. So this is the interaction of, okay, so this is the result of interaction of a rarefaction wave and a shock. Okay, so you observe certain things here. Okay, so this, after t bigger than 2, this constant state has just vanished. Okay, so only the first and last state of the initial data, namely 0 and 0, they are retained, and this one vanishes, and that is the region because of non-linearity. So we will not observe this in a linear problem. For example, if we have this ut plus ux equal to 0 and ux 0 is f of x, So at any later time t, this is just, so this it will not, so whatever the initial profile, it will be retained for all t positive. Okay, whereas in this case it's a non-linear problem, so that it changes the initial profile. In fact, there are results showing that as t goes to infinity, the solution uh, contains just an n wave, which I am not going to discuss. So whatever initially we have in this u0, more or less everything will be lost. Okay, because of this non-linear phenomena. Okay. And another thing we observe, so initially this line x equal to 1 plus t by 2 shown in red here. So the shock curve was a straight line, but after this interaction of rarefaction wave and this shock wave, that shock is made to bend. Okay, so now it's a curve. Okay, so it's 2t to the half. Okay, so it's, so this, because of that interaction, this shape of the shock changes uh, from t equal to 2 onwards. Okay, so these are some of the observations we uh, see here in the interaction of two waves. Okay, after this experience, so we can now try, okay, other interactions. For example, we can try that shock interaction. What happens? And so for example here we can take this u0x. How do we obtain such a thing? So just one example I am just giving. So this is 2 x is less than 0, 1 0 x less than 1, and again 0 if x bigger than 1. Okay, so the constant states 2 and 1 are connected by a shock wave, and again the constant states 1 and 0 are connected by a shock wave, and if they interactions, then what will happen? Okay, so that we can again study, but computations are not easy all the time. Okay, so we can also analyze what happens if two rarefaction uh, waves interact. And we can also examine, uh, so here the rarefaction was on the left and the shock was on the right initially, and that remained uh, later also. Okay, so this rarefaction remains, okay, and that shock also remains, though with some changes. Okay, certainly changes are there. And what happens if I start a shock on the left and rarefaction on the right? So that also one can try. So even whether it makes difference to have on the left side or right side. Okay, whether the interaction remains the same or is it different. Okay, all those things one can uh, do with some simple examples. Okay. So when we discuss this Lax-Oleinik formula uh, maybe in the next class. So you will not see any of these interactions in that solution. Okay. So it's for a general bounded initial data. Okay. So we appreciate that formula because it hides all these things uh, and for a just general bounded initial data. Okay, so it does not assume any of the Riemann problems and other things, but certainly using that formula, all these things can be again obtained. Okay, so I will stop here and next time we will take up Lax-Oleinik formula. Thank you.